Hello, Algebra 2 students. I appreciate you finding time to get your notes taken care of. Today we're going to be looking at different representations of square root functions. Some of you are getting pretty bad about skipping the title and the objective of your notes. That is a requirement. It's part of it, so please copy down your title as well as your objective. And our objective for the day is to explore alternate representations of square root functions. Okay, there's going to be a lot of methodology, okay, different strategies, lines of thinking, and stuff like that. So you may find it necessary to press pause to get some things scribbled down, and of course hit pause anytime you need to, and then hit play when you're ready to move on. Okay, so for the last couple of days here, we've been talking about the graphing of the square root functions. Okay, we've learned how to read the equations. We've learned how to run through the plotting method for getting these guys graphed. Okay, and we were basically picking values in order to plug into the equations so we could discover the ordered pairs that build the graph. The real issue is what happens if the equation is not known. You have to assume that the people that are going to write our test know that we are going to know how to graph based upon the equation. So we'd better know how to build an equation if one is not provided for us. Okay, so if we're going to assemble the equation based upon a graph or a table or a chart or a word problem or any of the other dozen ways that they can present these problems to us, okay, then basically what we're doing is we're using these same skills that we've been using for the last couple of days, but we're basically using them in reverse order. Okay, so let's take a look. Okay, there's a lot of different ways that information can be provided for us other than handing us an equation. Okay, a t-chart or an xy chart is a fairly typical alternate way that information about a graph can be provided to us. Okay, so let's say we're faced with this little situation. Okay, we have values in the domain and then they're matching values in the range. And we're going to start off with some fairly simplistic type of questions. Okay, such as, is this an example of a square root function? And if it is, what is a likely equation that would describe it? Okay, now I say a likely equation to describe it because chances are we're not going to be able to get to some of the precision answers that we might have if we had the actual equations, because some of the coefficients are difficult for us to read and understand at this point, but we should be getting better. So let's see how close we can actually get. Okay, let's just start off with this. Is this an example of a square root function? Okay, well, they have basically handed us points. Okay, and they are essentially asking us, is it a square root function? Well, we're going to use our plotting method. We don't even have to invent the points and plug them in. Okay, they're already handed to us. We can plot our points in our graph. We can connect the dots from there, and we can simply answer this question. Okay, is it an example of a square root function? We can answer this on basic intuition. Is this a square root function? Does it seem to obey the basic structure and behavior of a square root function? And based upon what we can see here, I think you'd have to say, yeah, this is a square root function. It does seem to be doing, generally speaking, what it's supposed to be doing. Now, its behavior is obviously altered in some way, but it's got the basic idea of a square root function. Okay, so let's move on. Okay, the second part of the equation, or the question, is what is a likely equation to describe it? Okay, well, let's see if we can't find some answers to that question. Okay, basically what we need to do, and this is why we spent so much time talking about the parent functions, we want to compare what the parent function should have been doing to what this graph actually is doing. Okay, so let's compare it to the parent function. So here I have brought the parent function, its first 5 ordered pairs, into the problem. There's y equals the square root of x. Okay, that's what our graph should be doing, but clearly it is not doing that. Okay, so let's see if we can figure out what is different. Well, just start making basic observations. Okay, one of the first observations that you might make is, okay, obviously the parent function leaves its vertex and heads upward. Okay, this new function that we have here is obviously not moving upward, it's moving downward. Okay, that's a good observation to make. But then you have to connect that to what should that do to the equation when it comes time to write it. What will the equation do differently because this new function is moving downward? Well, just think about it. Instead of following the positive y-axis, it's now following the negative y-axis. So we need to keep in mind that when it comes time to write the equation, the y values have been reversed. We're going to need to express that in our equation. Okay. Another thing to notice, a very easy thing to notice, is that the speed of the graph as it moves away from its vertex, these step sizes are obviously different. Okay, so we've got some height differences going on between the x-axis and the function as it moves away from its vertex. Okay, so what I've done next is I've just kind of compared some values. I said, okay, well, let me take a few measurements here. Okay, and these are just based upon the ordered pairs. You can see as you move over 1 unit on the x-axis, the parent function also moves up 1 unit, but this new function moves 3 units. Okay, next step over, the parent function moves 1.4 units. This new function, 4.2 units. Okay, and keep moving, you can see those values that are there. Okay, now hopefully you'll be able to identify that there is a pattern at work there. Okay, and that pattern would be that this new function is moving towards infinity 3 times faster than the parent function did. Okay, all of these heights are basically right around 3 times larger than the parent function had those same heights. Okay, so what does that mean to the problem? That means we're going to have a coefficient of 3 mixed in with our function, okay, our equation. So that's going to be something else to keep in mind when it comes time to write the equation. Okay, there's a couple of other things to consider. And if you think back to the questions that we asked back on day 1, okay, what kind of other stuff would we be looking for in the graph? Okay, well, left or right? Okay, are both of these graphs moving the same direction or are they moving in different directions? Well, clearly this time they are moving in the same direction. Okay, so they're both moving right. That means this new function did not change that about the parent function. So that's important. That means our x value is unchanged. X did not get a sign change. We need to remember that when it's time to write the equation. And also, they originate from the same place, so they have the same vertex. That's important as well. So we do not have to mess with h or k when it comes time to write the equation. Well, now it is time to write the equation. Okay, based upon these 4 observations, okay, our y value needs to be reversed. Okay, and we need to have a coefficient of 3. So what is a likely equation to describe this situation? Y equals -3 of x squared. We put the negative outside of the radical so that it can affect the y value rather than the x value. We said y should be reversed, but x should not. Okay, we did not have a vertex change, so we left it at 0, 0. And we did install the 3 outside of the radical so that it could be an effect of 3. If you wanted to put a number inside of the radical, the number would have had to have been 9, because the square root of 9 would have resulted in a 3 outside of the radical. Okay, so in all likelihood, this is probably the equation that described that set of points. Okay, now there's a lot of different graphical representations that we can face, and you know how our stuff goes. We are likely to face just about anything that the test writers can think of. Okay, so we saw a T-chart, an XY chart. Okay, now let's look at another type of graphical representation. Hopefully you remember this one. What's it called when you have 2 sets, typically shown in circles or ovals, and you have arrows drawing from one set to the other set to show how the values are interconnected? This is called a mapping. Okay, so we have a mapping here showing us some values in the domain connected to the values in the range. Okay, same 2 questions we're going to face. Is this an example of a square root function? If so, what is a likely equation to describe it? Press pause if you need more time. Let's get to the problem. Okay, if we take this information to a graph, okay, and here are, I've changed it over to an XY T-chart, okay, rather than the mapping. Most people are better at reading the XY T-chart as opposed to a mapping. Okay, so I've got 6 ordered pairs that were given to us in the problem. If we plot them, they look like this. Okay. Now the direction of the arrow on this square root function, basically all I did is I am supposing that it is moving leftward, okay, because of the way the graph is flattening out as it heads towards infinity. Okay, so it's just kind of an educated guess that the arrow is headed that direction. Okay, so the question, is it a square root function? Yes, it absolutely does appear to be a square root function. It might have some things going on with it. Clearly, it has been moved. Its direction has been changed. Okay, we might have a change in its speed, but it is absolutely behaving the way we expect a square root function to behave. Okay, so that's an easy part. Okay, just having a look at it and making that determination. Now, in order to figure out what's going on with the equation, once again, we're going to compare to the parent function. Okay, so the parent function, y equals square root of x, okay, is that orange guy that just appeared in the graph. Okay, and let's start comparing information. Okay, once again, very easy to compare the directionality of these two. The parent function is moving to the right, and our new function is moving to the left. So that's a very obvious change. Okay, so what kind of effect is that going to have on the equation? Well, very simple if you think about, okay, the parent function is following the positive x-axis. The new function is following the negative x-axis. So obviously we have an x-axis sign change. Okay, our x value is reversed. That's going to be important when we write our equation. Another very easy thing to notice is the origination point is different. Our vertex is not the same for both of these functions. Okay, now obviously the parent function wants to begin at the origin. So what is this one doing differently? Well, this one has a different k value. And how has k been adjusted? K has been moved down 2 units. That's going to be important when we write our equation. Okay, now we can also check the speed of the graph. The speed looks relatively similar. Okay, and if you compare them each to kind of their baseline, the parent function being the x-axis and this new function being the line y equals -2. If you measure those distances based upon their ordered pairs, you will very quickly and easily see that the values are the same away from those two lines. Okay, so it does not appear that there has been a speed change of anything or anything like that in the graph. Okay, so we're not going to have to worry about a coefficient this time. That's nice. Okay, so our speed is unchanged. Okay. And the fourth and final thing to worry about on this is the up or down direction. And it's very clear to see that both of these graphs are moving upward, okay, as they should be. That means that the y has not been tampered with, so our y value is unchanged. Okay, so let's have a look and see what the equation should say. Okay, we're going to have a k value this time, which means there should be a constant being added or subtracted to the end of our equation. Okay, and that value will be a -2. We said that the x value was going to have to be reversed, so that means underneath the radical, we're going to change the sign. So our equation should look something like y equals the square root of -x, that's going to send it to the left, and then -2 outside of the radical, that will drop the vertex down 2 units. Most likely, our equation is y equals the square root of -x -2. Now, if you're starting to wonder a little bit with me saying most likely the equation is going to read like this, and you're going, well, how am I going to know for sure? What happens if the answer choices are all very similar to each other? Okay, well, I find it probably unlikely that the answer choices will be very similar to each other. I think based upon these observations that we're making in the graph over and over again, you will get close enough to one of the choices to know for sure that that is the correct choice. Okay. Now, another way that our problems can show up is everybody's favorite. They can absolutely occur in stated form. Okay, so we are very likely to see word problems to go along with this stuff. This is the same information over and over again. They're just going to change the way they present it, would be my guess. Okay, so here's another situation. A scientist measured the results of an experiment. Nothing happened until 3 seconds has elapsed. At time 3, he had 5 grams of material. At time 4, he had 4 grams. At time 5, he had 3.6 grams. And at time 6, he had 3.3 grams left. He thinks this is a square root relationship, and he thinks the equation is y equals the square root of negative x minus 3 minus 5. Is he correct on these two hypotheses? Press pause if you need some time to copy that down, and I'm sure you probably do. Now let's take a look at the responses to the questions. Okay, does he believes that this is a square root function? Okay, well the problem gave us 4 ordered pairs. They just did not look like ordered pairs. Okay, keep in mind one of the variables being discussed in the problem was time. Time is always independent. Okay, so time always gets the x-axis. So I took time 3, 4, 5, and 6, and I gave them to the left-hand column, like the x-axis, the x-coordinate, the abscissa. Okay, and the amount of material that remained, the grams of that material, okay, 5, 4, 3.6, and 3.3, I gave them to the y value because that is the dependent value. The amount of material left depends upon how much time has gone by. Okay, there are the 4 points that are being shown in the graph, and this does appear to be a square root function. I did not connect the dots in my notes, but if you would please go ahead and connect them in yours. Okay, now it says he thinks the equation is y equals the square root of the negative x minus 3 minus 5. We want to see if he is correct. So once again, we are comparing this graph to the parent function. Okay, so let's start again. Let's look at the up and down of it. Okay, obviously the parent function is moving upwards. The other equation is moving downwards. Okay, that means one is positive on the y-axis, one is negative on the y-axis. So our y values are reversed. Okay, let's look what else there is. Our vertices, okay, the vertexes for the two square root functions are not positioned the same. Okay, so the vertex has changed. Okay, so if we go from the parent function to this new function, what is different? Now, obviously, the h value has changed. We've moved over on the x-axis 3 units to the right, and the k value is changed also, and it has moved up by a value of 5. Okay, so there's a couple of things we're going to have to keep in mind when it comes time to compare the equations. And remember, we got to watch out for signs with h and k, the way the formula is built. Okay, we can take a peek at the speed of the graph. Okay, once again, we'll look comparing the measurements based upon the ordered pairs that we know for the parent function and the ones that we know for this particular experiment, and we can see that the distances from their beginning horizontal line there, okay, they are the same. Okay, so we have no speed change. Okay, that's good. That's important. Speed is unchanged. And clearly both of our graphs are moving rightward, okay, like they should be. That means they're both following the positive x-axis like they should, so the x value is unchanged. Let's compare these results to our scientist friend here and see if he's got it right. Okay, we said the y values should be reversed. Okay, does his equation show a reversal of the y values? And it does not. Okay, his equation shows a reversal of the x values. Okay, so he's got something going wrong there. Okay, and let's see what else we got. We said that the vertex has changed. His h value should be right to the 3, and k should be up 5. Okay, have a look at his vertex in his equation. Does he have showing? Is that what he's got showing? Okay, he's got an h value of positive 3 because that negative belongs to the equation, so that is correct. Okay, x minus 3 is the correct notation there. And then he's got outside of the radical minus 5. Okay, is that correct for the representation of the k value? That one is actually incorrect. Remember, the equation is supposed to say plus k, not minus k. So if this says minus 5, that means that 5 must have been a negative the way it came into the equation. Shouldn't have been a negative 5, should have been a positive 5. So he's got a sign error there. Okay, so it appears that no, we disagree with the way he has this equation written. Okay, and instead he should have had the negative not under the radical with x, but outside of the radical so it could affect the y instead. And he did have a sign error on the k value. Should have been plus 5 to get that upwards shift. So as you can see, this is a little bit tedious, and it does take a little bit of brain power. You're just going to have to slow yourself down and pay close attention to what points are doing. Um, ask yourself, how is it comparing to what the parent function should do or should not do, and what kind of an effect will that have on an equation. Okay, we're going to spend a couple of days working on this particular material. This is important. I think probably the difference between success and a lack of success on our upcoming Unit 6 test, whenever we get to it, is probably going to be hinged between can we connect all of these different representations to the graphs and then to the equations themselves. Okay. Anyway, as always, I appreciate you finding time to take care of your notes. I apologize for the length of these notes. Not a lot of work in there, but a lot of explanation and a lot of talking and stuff like that. So anyway, I will see you in class. Have a good day.